everyone. I thought I'd take a few minutes and knock out a quick, typical, very simple machine learning regression model using R and R Studio. Now this is nothing special that I've built. This is just using a very typical data set called the Autos mile per gallon data set. You can find this tutorial just about anywhere. If you look for it, do a quick Google search. Like I said, it's nothing special, but and the process that I'm going to use is not really all that special either. I'm going to go through the typical steps of building just a simple linear regression model using a linear model function in R and an AutoMPG. We'll do a little bit of pre-processing, a little bit of cleanup on the data set, and then we'll knock this out. I'm going to go through this and I will explain what I'm doing along every step, and hopefully watching the video will be a little bit easier than reading through some of the tutorials that are out there. So I've already gone ahead and set up an RStudio project for this. I've got my data set sitting in the actual working folder, working directory as well. So I'm just going to import data set. A lot of people use Read CSV for this. If you want to go old school, a lot of newbies don't like to do that. It's a little bit simpler to use the Reader package for this. So that's what I'm using with import data set. This gives you a really nice preview of kind of what's going on. I'm going to go here and just change this over to Autos because I want the data frame to be called Autos. I'm not worried too much about data types or anything at this point because I am going to change a little bit of those. The only thing I'm going to do here is I'm actually going to leave out this car name column altogether. I'm going to change a few of these others and don't really need that in there at all. So I can go ahead and import this. By the way, this looks just like very similar to something like RapidMiner, this nice little preview screen. So older versions of RStudio don't actually have that in there. So in this this is very helpful in a visual way to import data. So we've got our data in now. We've got it as a global environment. You can see the data frame there. The first two things I always do with my data when I bring it into my process is the first thing I do is actually check the structure of it. I want to make sure that R has done what I needed to. Most likely it hasn't. It's not MindReader with the data types. So you can see miles per gallon is a number, cylinders numbers, displacement horsepower. You can see all the different data types there. You can also open this and see the data types of every single variable. And I want to change a few of these things over a little bit. I actually want cylinders to be a nominal variable. I want the model year to be nominal itself, and I want origin to be nominal itself because I don't want the linear model using those as quantitative variables. So you could do this at one swipe if you wanted to with lapply. I'm not going to do that. I'm going to do this just the simple way so you can kind of see what's going on. So all I'm doing here is using something called as factor. Now since this is each feature that I'm wanting to change here is already something else other than a factor, what I'm using is as factor to change it to a factor, and I'm literally just writing over the same thing again. So we'll just use autos here and cylinder, and I'm going to do this again, except this time I'm going to do it with model year. And again, you could do this with one swipe if you wanted to, using something like lapply. I'm not going to worry about doing it with lapply because, again, I wanted to really just explain every single step that I was doing during the video. So these three, what will eventually be features, are now, if we run a structure, we can see that we've got these really nice, we've got cylinders as a factor with 5 levels. That's just a categorical variable with 5 different categories in it. We've got model year as a factor with 13 different levels. And we've got origin as a factor with 3 different levels. Another one I can see in here, horsepower actually came in as a number. We don't want that to be, as a character. We actually need horsepower to be a number. So let's knock that out right quick. Do a little more pre-processing here. And again, we're just using this to overwrite the same thing, the same feature is all we're doing. So horsepower. Okay, now, anytime you get this problem where NAs were introduced by coercion, right? This can be a really big problem when you are trying to build a machine learning model. So what I'm going to have to do is check to see how many NAs were actually coerced into this problem. So the next thing I'm actually going to do anyway is check the summary of this data set. Data frame, if you'd like to call it that. So you can see that horsepower's got about 6 missing values in it. So we have to be very careful when we're dealing with features with NAs in them. There's a lot of different ways you can handle NAs in different columns. Since horsepower is going to be representing the number of horsepower in each one of these models of cars, I could do 2 things. I could just strip the NAs out if I wanted to. There's only 6 of them, but we only have 398 rows in this data set, so I'm not necessarily comfortable doing that. So I'm going to do something that's actually pretty typical, and I'm going to actually replace the NAs in horsepower with the mean of horsepower. Okay, so here we go. So the way we do this is we pick the feature with the NAs in it, and then we're going to use bracket notation to actually check to see if it has NAs in it. Autos, horsepower, like that. And then again, just like we were doing with as.factor, we're going to actually replace that with the mean, of the horsepower column itself, and then we'll just stick the tag in here, NA remove equal true, in case we have anything left over, like such. Okay, now let's run summary again. You can see horsepower is cleaned up and we're ready to go. We've got no NAs in horsepower, but we do have another feature in here that's problematic, and that's model year. Let's make sure none of these others, by the way. I'm looking for an other. You see this right here? Other. I'm looking for that in the bottom of these columns. I don't see any more. But model year's got 198 NAs in it. So, and the problem with model year, if you remember, model year is a factor. Model year is a category. I'm going to get rid of model year altogether. I could leave it in there, but quite honestly, something that's getting that high a number of classes in it, if I were going to develop this out a little bit further down the road, that's probably going to be something that's really high on the list as far as problematic and maybe even causing feature bias. So let's go ahead and just get rid of it. We can work through it later. Maybe I can build another video with it if you want. So I'm just going to assign it. No. Okay. Summary. We're clean. We've got everything ready to go here. Horsepower, weight, acceleration. We've got origin as a factor. And there's only 3 categories in it, which is great. Cylinders a factor. We've only got, looks like, about 5 categories in cylinder, which is good. Everything else is numbers. We're good and clean and pretty much ready to go. So let's dive into actually building our simple linear model here. So to do this, the first thing we need to do is break this data set up into a train set and a test set. Now we're going to build a machine learning model off of this, and to assess that machine learning model, make predictions, we actually have to have a separate test set of data. Word of caution here, this is a really small data set, and sort of out in the wild or the real world, this would probably be really too small to do much with. But as it is a training exercise, hopefully you can take that with a grain of salt. So I'm going to just set this as train size. What I'm doing here is actually taking the number of rows of my autos data frame, and I'm multiplying those by 0.70. And basically what that means is I want the first 70% of the data in autos to be my the size of my train set. So that's what that means. Make sure our parentheses 2, 2, 2, everything looks good there. Let's do the same thing here with test size. We're not building it yet. We're not building the actual training and testing sizes yet. Training and testing sets yet. We're setting up the actual procedure to do that. And this is train size. So basically what this is doing is saying, hey, look, take the rest of the rows that are left over, which is the other 30%, and use those for your actual test size. Okay. So now if you really wanted to see, kind of what these are, and again, this is pretty much in every tutorial like that out here. You can see that my train size is 279 observations. My test size is 119 observations, right? So that's about 70 and 30%. So now I actually want to get ready to build my actual train set and my test set. And the reason I haven't done that already, the reason I'm not just taking these two that I've sort of done, if you will, is because these are ordered. If you look at the actual data in train size and test size and actually print it out and look at it, there is an order, a natural order to those that is a result of how the data was actually recorded. So we have to get rid of that ordering. We don't want that ordering to create any type of bias when we build our linear model. So we're going to sample the train size and pop out a train set and a test set based on the sample row numbers that come out of the sample. So let's do that. So anytime we're creating any type of a random sample, or we're using the random number generator inside of RStudio, we have to basically give it a set of instructions or an identity to follow. So every time I run that random number generator, it's going to use that same identity. Now I only have to set this one time per running session of R. I don't have to do this every time I use it. But if I use a random number generator on my specific project, and I turn around and I have a buddy do that exact same thing, but the way they set up their random number generator identity is different, the results are going to be different. So this 1, 2, 3 that is here in set seed is literally just sort of that identity on how you want the random number generator to start its calculation. So if I use 1, 2, 3 and my buddy uses 1, 2, 3, and the exact process is the same from that point forward, my model and his model or her model, our results will be the same. So that's what set seed is. So you're not going to get any results from set seed. You're just setting the actual seed. It's a global variable that you're setting in the back end. So now I actually want to grab the row numbers to start building my train and test set. And I'm going to do this again by building an actual sample. And I'm going to use the in rows of autos again to do this. But this time, I've got too many in here. This time I'm going to use train size, which is what I built a few minutes ago. And let's see, I think I might have too many in here. That feels right. And that feels right. And I've got one more here. Okay. Something's wrong because that's just not the case. Okay, so 1, 2, 3, 4, 5, 6. And go back to end rows. There we go. Okay, good. Now, so if I type in training indices, those are actually the random row numbers that are coming out of the sample. Okay, so by using those to build my train set and my test set, I know everything has been randomly stratified. So I don't need to worry about anything that's being ordered anymore. So now, I'm going to build a training set. And I'm going to use autos. And I'm going to use these training indices for the actual rows. And then I'm going to use testing, autos. And what I'm going to do here is basically the inverse of that, which is again kind of everything that's left over. You see this? This is row column indexing right here. This is if I was really writing this out, it's row comma column. You can see that because training indices are row numbers, I'm basically telling it take all of the training indices up front for training, and what's left over, sort of the opposite of those, which is the other 30% for testing. So now if I look at training, okay, there is my train set that's been randomly stratified. And if I go out here and I look at testing, same thing. Okay. All right. Now we're good to go. Let me give us a little bit of room here. And we're ready to build our model. Now we're going to use just a regular linear model for this. Linear model comes with R base, so you don't have to worry about bringing any packages or anything in that. And the formula that we're going to use is pretty straightforward too. So I'll make some references to another package out there once we actually jump out to build this. I like to use this particular sort of nomenclature. If I'm going to be using a linear model to build my model, I like to call it LM model. Many times too, I'll go ahead and put a 1 out here if it's the first time I've built this model. Maybe I'm building multiple models, right? If this was something with actual parameters in it that I could tune, maybe I'm building multiple models of those and tuning parameters. So you'll see me call it LM model. You'll see me call it LM fit as well. So this is just a regular linear model, and this has this formula equals. You're going to see in different packages, different machine learning packages, sometimes this is written this way, and basically what this formula equals here is this is your actual label. This is your dependent variable that your machine learning model is asking you for. So it's going to give you an option to specify the dependent variable and either all of the independent variables or features or predictors, whatever you'd like to call them, or a set of those. And in our particular case, we just want, we're going to do MPG for this. We just want just the name of the dependent variable, and then we're going to do tilde period. That tilde period tells this particular formula notation, use everything else as features. If I didn't want to do that, I could come in here and remove this period and actually put the features that I wanted to use as individual features if I didn't want to use all the individual features. But here I want to. And for this, we're just going to use data equals training. Sorry guys, I left a comma out here. There we go. Okay, so we've built our linear model, and you can see here it is right here. We've actually built this LM model that's sitting in our environment right now. So if I want to go out and I want to take a look at that, by the way, let me back up one time. If I was using something like Caret, like the Caret package for this, and a lot of other sort of more modern packages, if you will, this formula piece doesn't actually have to be in here. You could actually just write it just like that. So you could take formula equals right out of this. This is an older kind of school way of doing things, and you used to see a lot of packages were written like that. So you don't necessarily have to write it like that, but if you see it done that way, then there it is. It means the exact same thing. So if we take a look at our model here, we've got a residual standard error of 3.972. We've got a multiple R squared of 0.75, and what that means is this model can understand about 75% of the variance in the data that you've trained it on, which is, that's not too bad, about 3/4 of the data. You've got a p-value, a really low p-value, which means the features in this model are statistically significant when it comes to actually building or actually being impactful to something like miles per gallon. So not too bad. In this particular one, you got some other stuff up here too. You got coefficients, kind of tells you how useful some of these other individual features and levels are when it comes to miles per gallon. That's pretty good. Last but not least, if we wanted to actually go in and make predictions with this, we can. Just using the regular predict function inside of R. This is not anything fancy, and all I'm doing here is using the model that I just built and the testing set. And if I wanted to actually see what those are, I could take a look at them. There they all are. Now, what I would need to do to know how well this model actually worked is compare each one of these predictions, right, to each one of these, because these are actually the real values, the ground truth in your test data. You can see right off the bat here. I'll make this a little bit larger, and you could build a spreadsheet and compare these two if you want to, or you could use something like MAPE. The average percentage error between these two. You can see right here the prediction of the 119th observation, and the predicted values was 28. Was 27. The real value, actual ground truth, was 28. 118th was 28.36. The 118th was 32. Jumping up here, you've got a 38. That's a real value. My model predicted 21. You got another 38 up here. That's a real value. My model predicted 33. So you can see where some of the error is coming from in this particular model. So that's it. Soup to nuts. The only thing left to do is really evaluate how well the model did in the predictions. Like I said, you can use MAPE to do that. If you want to compare, sort of calculate your own cost function between the predicted values and the known values. If you're using something like the Carrot package, it has a great function in it called post resample, and that's exactly what it does. It gives you, it measures the ability of your model to make predictions on the predictions versus the ground truth, and actually gives you the same metric as you train the model in. So you might get an R squared and an RMSE back for a regression problem, or accuracy in kappa for a classification problem on the training and the testing model, which is pretty cool. So anyway, hope all of you enjoyed this. Hope I made it simple enough where you can understand sort of what's going on. I'll clean this up a little bit and get it out there for all of you. And absolutely, if you've got comments about it, please put those in the channel. Love to hear from you, and be sure and subscribe so you can kind of keep up with what's going on in my world. Thanks, everybody.